Hi all, welcome to the next video on design of beams, that is module number 5. Before we start with, it is better to have these notes, that is module 5a design of beams and module 5b design of beams, as well as IS 800 2007. Now coming to the directly content of that beams already you know, beams when they are subjected to the loads, they will be subjected to what? Bending, that is flexural. That is if you remember your RCC theory part, it is combination of what? Tension and compression. When it is subject to any beam, when it is subjected to bending, so the bottom layers are subjected to tension and the top layers are subjected to compression. Coming to the theory, the other part, design of flexural members. Now it is designed as per IS 800. It is designed as per section number 52. We'll go to the other clauses in detail when we take up a problem. Now the behavior or the failure of the flexural members. The first one is flexural failure. The flexural failure, which is already are aware just now, like discussed, it will be subjected to the combination of tensile and compression. Clear? Next is shear failure. Clear? Now beams are also subjected to shear failure. So mainly supports will have, usually in case of simply supported, will have a maximum shear failure pattern. Then the next failure pattern is torsional failure. The next type of failure is torsional flexural bending. The beam will be subjected, you can see this figure here, the beam will be subjected to the torsion along with bending. Now this is pure bending. So along with bending, it will also be subjected to twisting or torsion. The first flexure bending, shear bending and torsional bending are called as the overall failure of the member. The first three, flexural bending, shear failure and torsional failure, are called as overall failure of the member. Member fails as a whole. The other two types of failures are web buckling and web crippling. Web buckling in the sense, here if you assume this as an I section, if you look at this I section, so now web will buckle locally, though the flanges are stable or strong. So web alone is failing by buckling. There will be overall failure of the buckling of the web, or else it will be by web crippling. There will be local failure of the web. Now these two happens because of the maximum shear forces acting. At the supports or point loads, the point loads acting on the beam. Now these three are the overall failure members, and these two are called as local failure. Local failure happens because of the maximum shear force acting at the supports, or as well as at the point of high concentrated loads. Mainly the web buckling and crippling occurs because of the slender nature of the web. The web buckling and the crippling occurs because of the slender nature of the web. The slender in the sense, the thickness of the web is very much small. So here you can see this figure. The thickness of the web is very much small compared to the depth of the web. The thickness of the web is very much small compared to the depth of the web. Clear? Now web will try to buckle like this, which is called as web buckling, or will try to fail locally, which we call it as web crippling. So whenever you design, the other last failure is one more is missing, by deflection criteria. The other type of failure is deflection criteria. So that also you can note down here. So totally there are 5 to 6 type failure patterns. The first three are called as, and as well as the deflection is called as the overall failure, and web buckling and crippling are called as the local failure. Now coming to the stresses in I section of a beams. Now you might have already come across the stresses in rectangular section. So you will have a linear stress variation. The bending stress if you take a rectangular cross section, you will have a linear stress variation. But in case of I section, so this will be the bending stress pattern. In case of an I section, an I beam, so this will be the bending stress pattern. So you can observe that the major bending stresses are taken by the flanges. You can see these are the major bending stresses which are taken by the flanges, and this is the bending stress taken by the webs. Now compared to webs, flanges takes the major bending stress. Flanges take the major bending stresses, that is top flange as well as bottom flange. The webs take a very minimum amount of bending stress, or they resist the very minimum amount of bending stress. So one thing you should understand here, the major, it is not what is that, bending stress is majority of the bending stress is resisted by the flanges. Coming to the shear stress, here you can observe, now shear stress here in the top flange and bottom flange it is less, but it is more in the web. It is more in the web. It means that the majority of the shear stress is resisted by the web. Majority of the shear stress is resisted by the webs. Now these two figures you should keep it in mind. The shear stress is mainly, the majority of the shear stress is resisted by the webs. Flanges also will resist the shear, but it is very minimum. Now what is that we are concluding here? The majority of the bending stress is resisted by the flanges, and webs resist the very minimum bending stress, and majority of the shear stresses is resisted by the webs, and flanges resist the very minimum bending stress. Now coming to the types of beams. There are two types of beams. One is laterally supported beam. Other one is laterally unsupported beam. Now for your study you have is only the laterally supported. For your study you have is only laterally supported beams. Clear? And same time you are not studying or not going through in detail of the laterally unsupported beams. First you should understand what is laterally supported and laterally unsupported. Now if the top flange of the beam is flushed or what you can call it as concealed in the slab, if the top flange of the I section, if it is concealed in the slab, it is called as laterally supported or something like this. There is a, what you can call it as, an angle section which is welded to the top flange, is inserted in the RCC slab, clear, is called as laterally supported beam. Now this arrangement will allow the beam to bend in only one direction, that is about x-axis. A laterally supported beam will bend in only one direction, that is about x-axis. And the laterally unsupported beam is that the slab will be just resting on the I section, flange of an I section. It is nowhere connected. The top flange of the I section, is nowhere connected to the slab above that. This slab will be simply rested. So in that case, what happens? There is no connection between the top flange and the slab. There is no connection between the top flange and the slab. Hence, the beam, this becomes an laterally unsupported. Hence, the beam bends in x direction or bends about x-x axis as well as y-y axis. X-x axis as well as y-y axis. Now, I'll quickly repeat once. Now, laterally supported beams are those beams. Wherein your slab is concealed, the top flange of the beam is concealed like this, or an angle section will be provided which will be welded to the top of the flange, and that angle section will be inserted in the RCC slab supporting that. So in such cases, the beam is called as laterally supported, which will bend only about the x-x axis. And whereas for laterally unsupported beams, the slab is simply made to rest. There is no connection like this. In case of laterally unsupported beam, the slab is simply made to rest on the top of the flange of I section. So in this case, beam will bend both in x direction. Beam will bend both about x-x axis as well as about y-y axis. Now you need not bother much about this. For your study, you will be having is only laterally supported beams. Yeah, now laterally supported beams. Now coming to the design of laterally supported beams. Now it is checked for two cases. One is webs susceptible to buckling. Now you can also refer to the clauses. Webs susceptible to buckling and webs are not susceptible to buckling. So now webs susceptible to buckling in the sense the tendency of web to buckle like this. So if d by tw, so d happens to be the depth of the web. Clear? How do you calculate this? This will see much in detail when we take up a problem. So this d is nothing but what? Overall depth minus thickness of the flange, thickness of top flange and bottom flange. So d by tw. Tw happens to be the thickness of web. If d by tw is greater than 67 epsilon, then your web is said to be buckling. So in that case, the design has to be done as per 8.2.1.1. If d by tw is less than 67 epsilon, we'll all see what is epsilon value and all in bit later cases. If d by tw is less than 67 epsilon, if d by tw, if it is less than 67 epsilon, so webs are said to be, webs are not susceptible to buckling. Yeah. Then when your webs are not susceptible to buckling, so then there are again high shear and low shear criteria. So high shear and low shear criteria. Now this clause again we'll see when we take up a problem. Yeah. Now this is all about the theory part. Clear? And now what is that two main? Yeah. Now quickly we'll brief. Now these are the failure patterns which are classified as overall failure and local failure. The one more failure is failure by deflection. That also has to be added here. The failure by deflection pattern. Yeah. The same. Yeah. Now coming to the stresses. Now this is the bending stress. The major bending stresses are resisted by the flanges. As you know, you will have the combination of compression and tension in case of bending stresses. So major bending stresses are resisted by the flanges and very minimum stresses are resisted by the webs. Now coming to the shear stress, the major shear stresses are resisted by the webs and some minimum shear stresses are resisted by the flanges. Coming to the types of beams, that is laterally supported and unsupported beams, which for your study you don't have laterally unsupported beams. So you have is only the laterally supported beams. Now within that laterally supported beams, there are two criteria: web susceptible to buckling and web not susceptible to buckling. And within web not susceptible to buckling, there are two more criteria, which will be seen much in detail when we take up the problem. Now, whatever discussed, the same thing is also mentioned in this theory part. The other module 5a, the module 5a design of beams, whatever we have discussed, we have briefed here. Whatever brief description we have shown here, so that itself is done in much in detail explanation is done here. You can just read that and explain in your own words. Yeah, web buckling, which is we spoke of. Local failure, that is web crippling because of the point load. Then web buckling. Yeah, this is web buckling. Whatever we just now briefed earlier. So that is all how the design has to be done. We'll not be worrying much about that. We'll be seeing anyhow in detail. Yeah, the design of this shows the design of laterally supported beams. The design of laterally supported beam. The design steps are given here. Yeah, now you can refer to this also. This is important. Design steps of laterally supported beams. Laterally unsupported beams you need not study. This is not there for your study. Laterally unsupported beams need not be studied. Yeah, the deflection, there are standard deflection formula you should understand. This deflection of simply supported beam subjected to UDL, the maximum deflection will be at the center, that is 5 by 384 into WL to the power. This is L to the power 4, this is L to the power 3, L to the power 3, L to the power 4 divided by 8AI, that is cantilever subjected to UDL, cantilever subjected to point load. Yeah, now that ends up with the video lecture 1 on design of beams. In the next lecture, that is second lecture, we'll be taking up the problem on the design of beams. Thank you.